In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller
All right, hello and welcome to Research and Reading Night over at Ether Cosmology. Tonight we're going to be getting into a paper by Ionel Dinu titled Trouble with Maxwell's Electromagnetic Theory, Can Fields Induce Other Fields in a Vacuum? So without further ado, I'm just going to go ahead and get into it. All right, so from our boy Ionel, shout out to Ionel. Abstract. The purpose of this article is to point out that Maxwell's electromagnetic theory, believed by a majority of scientists, a fundamental theory of physics, is in fact built upon an unsupported assumption and on a faulty method of theoretical investigation. The result is that the whole of the theory cannot be considered reliable, nor its conclusions accurate descriptions of reality. In this work, it is called into question whether radio waves and light traveling in a vacuum are indeed composed of mutually inducing electric and magnetic fields. This study is addressed to a small percent of students and researchers who suspect that there is something wrong with the way in which we understand nowadays, quote, how radio waves are generated and how they propagate in space. I know that there is always a feeling of distrust among students when the university professors obtain an equation of a wave from the four of Maxwell's equations. I've felt that myself as a student and have seen it again in open courses made available on the internet by prestigious universities of the world. Students ask pertinent questions and the professor fails to address the issue. And he gives a link to a YouTube video here that we're going to skip over, but I'll link it in the chat. You guys can check it out. 1 second. And in the video, I'll give a quick summary of it because I watched it earlier. There's a student in a class, there's a professor professing, and the student asks him about this, the self-induction of the fields. And the professor gives an analogy and says, well, you know how when you're a kid and you're dependent on your parents, and then you move out and you can just kind of be on your own. So that's what that was the answer that he gave, which is, pretty unsatisfactory. So anyway, when still a student, I promised myself that someday I would get back to the subject of radio waves and analyze it piece by piece, statement by statement, equation by equation, and I will not declare myself in agreement with the theory if I discover unfounded assumptions, guesswork, or things contrary to experimental observation. I can say that I have found each of these things. Oh no! What I consider most controversial is in all the present conceptions regarding radio waves is the belief that the electric and magnetic fields produced in and around an antenna by the charges moving in it induce each other and create new fields at other points of space. Even in regions of space, such as a vacuum where there is no electric charges, and that the field becomes self-sustaining electromagnetic waves. The majority of physicists and engineers agree with this description. No wonder, since they were good students and learnt what they could from their teachers and the textbooks available to them, all expounding the same doctrine. In this work, I will argue that the idea of electric and magnetic fields inducing each other without the mediation of electrical charges is false because it is not based on experimental evidence. Pure electric fields, varying or not, are known to produce pure magnetic fields in a region of space where the electric charges do not exist. Neither pure magnetic fields are known to produce in regions of space where the electric charge do not exist pure electric fields. It is only through the mediation of the electric charges and the currents that these phenomenon can happen. I will take excerpts from the works, mainly textbooks, of the authors who support the present day theory, and I will point out where their argument fails. What produce radio waves is known, rapidly changing electric currents in a conductor. But what is not known with certainty is how exactly the radio waves are generated from these changing currents, how these waves detach themselves from the antenna, and what the radio waves really are traveling through, or what they really are when they're traveling through space. These, I contend, are problems still open for argument and will be discussed here. My alternative explanation is that radio waves in a vacuum are simply mechanical waves in the ether, and that's filling the vacuum and produced by the charges, electrons, surging in the antenna. This view contradicts that purporting that radio waves and light are composed of electric and magnetic fields that oscillate and induce or otherwise create one another in a vacuum. But this article is about Maxwell's theory and the fact that it contains a faulty method of theoretical investigation and claims unsupported by experiment. I hope that what I have to say about the theory will make you eager to study the subject for yourself with more attention than you did when you were a student and had to accept it because your credits to graduate the university depended on it. And preferably develop a personal opinion on what is believed to be one of the most important theories of physics. I have offered some alternative ideas throughout this paper. It was without any other intention than to show that there are other possible ways to look at the problems discussed. Since this work is a critique of Maxwell's theory, the reader should not dismiss the latter just because he does not agree with the former. In fact, I warmly invite anyone interested to discuss their objections I raised, or whether the objections that I raised are founded or not, in the hope that through that kind of debate, Maxwell's theory will either come out strengthened or be replaced altogether by another that makes more sense. Mainstream science considers these matters settled beyond question, and I do not accept the great interest in this work from professional scientists. Or I do not expect great interest in this work from professional scientists. My hope is only that the young student, the young researcher at the beginning of his career, or scientist who want to remain true to their profession will have enough time to ponder these questions. My intention is not to demolish something that has value, that is valuable, but is to find true answers to the questions posed and avoid the
perpetuation.
Thank you. Perpetuation of the false ideas of the flawed reasoning in the physical sciences by turning a blind eye to what I believe is inaccurate. I consider my duty as an educator towards the science itself, towards science itself, and towards present and future scientists.
Just before we go any farther, that YouTube link that you pointed out way back, the one you were covering, is actually a 1 hour long file. And when you guys launch it, you might get a reaction that it's not a valid link. And you can cure that by adding an S to the HTTP part of the string. So change HTTP to HTTPS, and the rest of it will load as expected.
Thank you, sir. And then the timestamp he gives also is at the 35-minute mark, too. Forgot to include that. That's when the student asked the question.
Yes. Out of the hour. Very good.
Yep. All right. Section 1. What standard textbooks say? I know that it may be some time since you have graduated the high school. But I want to remind you how little standard textbooks for secondary grades have to say about radio waves and how they are generated. I start with some excerpts that deal with this topic. A, first category, textbook. These textbooks are written for secondary students, grades 9 through 10. The two examples chosen below give one single sentence, some information about what produces the radio wave, and nothing is said about how they are generated. So here we have citation 1 by our boy Tom Duncan. So radio waves. Radio waves have the longest wavelength in the electromagnetic spectrum. They are radiated from aerials and use used to carry sound, picture, and other information over long distances. The radio waves are radiated from aerials. All right, so being very vague there. My boy Stephen Popel. Radio waves. Stars are natural emitters of radio waves. However, radio waves can be produced artificially by making a current oscillate at a transmitting aerial antenna. In a simple radio system, a microphone controls the current to the aerial so that the radio waves pulsate. The radio receiver, the incoming pulsation, controls a loudspeaker so you can produce a copy of the original sound. Radio waves are also used to transmit TV pictures. So here he points out radio waves can be produced artificially by making a current oscillate in the transmitting antenna. Section B. Second category, advanced level A physics. So these textbooks are written for secondary students, grades 11 through 12, taking a physics course and finishing the GCSE. They discuss more technicalities, but are still silent about how the waves are generated by the current or charges oscillating in the antenna. So citation here. Radiation of electromagnetic waves into space. Consider an oscillator with a connected transmission line, and suppose the transmission line is bent as shown in figure 39.23i. So here we got our oscillator, got our antennae, voltages and currents running through it. The charges move along A to B are forced up to A, 1/2 cycle of oscillation, and down to B during the next half cycle. The charge therefore oscillates between A and B. This accelerating charge radiates energy in the form of electromagnetic waves. In contrast, charges move along the lines when a steady speed is created. Create a static magnetic field, and no electromagnetic wave is radiated. Accelerating charge radiates energy in the form of electromagnetic waves. 2, we have Chris Hamper here on standard level physics developed specifically for the IB diploma. So creating electromagnetic waves. An electromagnetic wave can be created by passing an alternating current through a wire as shown in figure 15.2. Waves created in this way are called radio waves. James Maxwell found that it was not the moving charge that caused the magnetic field, but the changing electric field that caused the charge to move. This explains how electromagnetic waves can travel through a vacuum. The changing fields induce each other. Maxwell also calculated the speed of the wave in a vacuum that was approximately 3 × 10⁸ meters per second. This value was about the same as the measured value for the speed of light, so close in fact that Maxwell concluded that light was an electromagnetic wave. And here we got some alternating current producing some radio waves, electric field, magnetic field, and comes out to be a radio wave. Here we find for the first time 2 statements that seem inconsistent with one another. The first is an electromagnetic wave can be created by passing an alternating current through a wire. Waves created in this way are called radio waves. The second is Maxwell found that it was not the moving charge that caused the magnetic field, but the changing electric field that caused the charge to move. What is the student supposed to understand from these statements? It seems that the electric current are not only anymore as the primary cause producing the radio waves. The primary cause for production of the radio wave has been shifted to the changing electric field that produces the oscillating current. Thus, the textbook tells the student something new, that a changing electric field generates a changing magnetic field. But is this true? Can a field produce another field? The textbooks say that this was found by Maxwell, but did Maxwell prove what the textbooks say he found? Sadly, the answer turns out to be no. Not only that Maxwell did not prove it by any experiment, but nobody proved it experimentally in the 150 years that has passed since then. What Maxwell did was a mathematical manipulation, which we shall discuss later. Why is this important? It's important because Maxwell's findings is used as to explain why electromagnetic waves can travel through a vacuum or even exist as a system of electric and magnetic fields in a region of space, such as a vacuum where there are no electric charges whatsoever. This explanation is, quote, the changing electric fields induce each other, end quote. It is meant that after being created by the original charge that oscillated in the antenna, the electric and magnetic fields continue to create and induce each other and exist in even regions where they're far from the antenna in space, where there are no electrical charges at all. The following section, I will argue that this picture is inaccurate. In closing this section, and before we discuss what mathematical manipulations Maxwell did and why he did it, there is the obvious fact that shows that electromagnetic waves are not produced by the changing by the electric field. Look at the antennas that we use. They are all conductors. If the primary source of the radio wave would be a varying electric field, which would then induce a magnetic field, which would then in turn induce another electric field further away, and so on and so forth, we would use for our antennas huge capacitors and not conductors. Our antennas would look like two huge metal plates separated by a dielectric, so air, and connected to the source of the oscillating high voltage. But this is not the case in practice. Even since the times of Hertz and Marconi, radio waves have been produced by discharges, which are sparks between the knob of the induction coil. And then we have a citation here.
He's referring to the telegraph there.
Yep. All past experimentation comes to demonstrate that if the electric current is not made to move violently in the conductor, no radio waves can be released into space. Section 2. Changing fields do not induce each other. A. Where is Maxwell not correct? Since the previous textbooks did not say how James Clerk Maxwell found the change in the electric field. Let me start over. Since the previous textbook did not say how James Maxwell found a changing electric field can produce a magnetic field, we will take another more advanced textbook designed for undergrad students by David Griffith, Introduction to Electrodynamics, from Prentice Hall in 1999. It is a well-known standard textbook that many physics students have used in their studies. This section makes a heavy reference to it. We discover from the textbook that Maxwell introduced the idea that the changing electric field can produce a changing magnetic field by modifying the experimentally found Ampere's law. At pages 321 and 326, we read the following. Maxwell's equations, electrodynamics before Maxwell. So far, we have encountered the following laws specifying the divergence and curl of electric and magnetic fields. We got our boy Gauss's law. We got a no-name law here. We got Faraday's law and Ampere's law. These equations represent the electric and magnetic theory over a century ago when Maxwell began his work. This set of equations has been changed by Maxwell. Section 7.33, Maxwell's equations. In the last section, we put the finishing touches on Maxwell's equation. So all these look the same except for this bottom one here that's been changed, where he's made a modification to Ampere's law and added this. This is called Maxwell's displacement current. So this is epsilon naught times mu naught over the derivative of the electric field over the derivative of time. Observe that Ampere's original law, nabla times B equals nu, or nu naught times, or mu naught, times J, which is a mathematical description of the experimental findings relating to the magnetic field B and the current density J producing it, has been changed by Maxwell by adding a supplementary term to the right-hand side of the equation, which is this little bad boy over here. Maxwell's addition is mu naught times epsilon naught over E, or times E over T, which has received the name Maxwell's displacement current. Ampere's original law allows the calculation of the magnetic field B produced at any point, or at a point in space, by the currents J flowing through the curves in space. It has experimental roots in Oersted's great discovery.
Yeah, that's Oersted.
Oersted, thank you. Oersted's great discovery that the electric current produces a magnetic field in the space around it. If another term is added to this equation, it follows that the magnetic field can also be produced in the manner described by this new term. Adding the displacement current to Ampere's original equation is equivalent to saying that a change in the electric field can produce a magnetic field B. Maxwell's modification of Ampere's law by the addition of the supplementary term is not correct.
Hold on a second.
What's up?
Can you scroll back up for just a sec?
Mm-hmm.
Back to that paragraph you just read. So he's saying that Ampere's original law, right? You got a magnetic field and it's produced by the currents, moving currents, right? And then Oersted had a discovery that an electric current produces a magnetic field, which we all know that's moving charges, right? So where does this term come from? Because the thing I'm wondering is that if nabla cross B equals mu naught times J was already correct, then adding an extra component, how does that not change it? Like, how could it be mathematically correct if it was correct before and then they added a term later?
Well, they needed.
We keep reading. It just seems interesting.
Yeah, they needed another part of the story, I guess. So B, why is Maxwell not correct? Maxwell is not correct for the following reasons. 1, such an effect that the changing electric field E can produce a magnetic field B has never been observed experimentally. Therefore, adding the term Maxwell's displacement current to Ampere's original equation is pseudoscience. 1 second. To see how absurd the matter can get, observe that you obtain a magnetic field even if there is no electric current at all. Where J equals 0, Ampere's law, modified by Maxwell, becomes nabla times B equals nu naught times epsilon naught, the displacement current again. This is the electric, since the electric charges, static or in motion, do not appear in the equation says that the pure electric field E, varying in time, can create a pure magnetic field B. This is pseudoscience because experiments show that the fields are created by charges, and an electric field E is created by a static charge, and a magnetic field B by moving a charge. Every time there is a field, this field can be traced to an electric charge at rest or in motion. The equation above, however, implies that the charge and currents are not necessary for the creation of the fields, and that one of the fields, varying with time, can directly, by itself, without any other means, without aid of mediation of something else or other than itself, creates another electric field, or magnetic field, creates the old B field. According to Coulomb's law, nabla times E equals rho over epsilon naught. The electric field E can change in time only if the charge density rho changes in time, but it is not apparent anymore in Maxwell's modification of Ampere's law. Note, Faraday's law seems to indicate another way in which the electric field E can be changed, but this is only apparent. As will be discussed later, Maxwell modified Faraday's law by making the same conceptual mistake as he did when he modified Ampere's original law. For what Faraday observed is that the changing magnetic field B induces an electric current J and not an electric field E. So the mathematical rendering of Faraday's law is also questionable, but we'll discuss that later. Part 2 of why Maxwell is not correct. Maxwell's displacement current is not an electric current. If there are supplementary currents to be added in Ampere's law, we will see later that one supplementary current must indeed be added. These currents must be added as currents, not as something else, because that is what the observation shows. Moving electric charge produces a magnetic field around them, a current, more accurately. Current density, because Ampere's law is written in terms of J, the current density is defined as J equals rho times V, where rho is the charge density and V is the velocity of the charges. C, how should Maxwell have corrected Ampere's law? Maxwell produced his displacement current in Ampere's law in an attempt to make it more general, i.e., to comply with the equations of continuity for electric charge. Look at the examples or explanations below, which will start with repetition of an excerpt of David Griffin's Introduction to Electrodynamics from 1999, as shown above. So here we're looking at the same thing as earlier. Yeah, it's pretty much the same. Actually, I'll just read it. 7.31 electro. Yeah, sure.
Okay. So far, we've encountered the following laws specifying the divergence and curl of electric and magnetic fields. We've got Gauss's law. We have the Nabla dot product of the Nabla times B equals 0. We've got Faraday's law, and we've got Ampere's law. These equations represent the state of electromagnetic theory over a century ago when Maxwell began his work. They were not written in so compact a form in those days, but their physical content was familiar. Now, it happens that there's a fatal inconsistency in these formulas. It has to do with the old rule that divergence of curl is always 0. If you apply the divergence to number 3, everything works out. So he when he does the Nabla dot product, that's the divergence, right? It ends up the left side is 0 because divergence of curl is 0. The right side is 0 by virtue of equation 2. But when you do the same thing to number 4, you get into trouble. The left side must be 0, but the right side in general is not. For steady currents, the divergence of J is 0. But evidently, when we go beyond magnetostatics, Ampere's law cannot be right. Hold on, because scroll back up. Okay, because you have the left side would be 0, but right side, all you have is, if you have a not steady current, like a time varying current, right, then the divergence would not be 0. So the right side wouldn't be 0. It was time varying. Okay. Of course, we had no right to expect Ampere's law to hold outside of magnetostatics. After all, we derived it from the Biot-Savart law. However, However, Maxwell's time, there was no experimental reason to doubt that Ampere's law was of wider validity. The flaw was a purely theoretical one, and Maxwell fixed it by purely theoretical arguments. How Maxwell fixed Ampere's law. See, the problem is on the right side of equation 7.35, which should be 0, but it isn't. Applying the continuity equation and Gauss's law, the offending term can be rewritten, that the divergence of J can be rewritten as negative divergence of epsilon naught times the time derivative of the electric field. It might occur to you that if we were to combine epsilon naught with the time derivative of the electric field with J in Ampere's law, it would be just right to kill off the extra divergence. Such a modification changes nothing as far as magnetostatics is concerned. When E is constant, we still have Nabla cross B equals mu naught times J. In fact, Maxwell's term is hard to detect in ordinary electromagnetic experiments, where it must compete for recognition with J. That's why Faraday and the others never discovered it in the laboratory. However, it plays a crucial role in the propagation of electromagnetic waves, as we'll see in Chapter 9. In my opinion, there is a correct and honest way in which Ampere's law can be fixed and make it comply with the equation of continuity. It starts from the following idea. How must the current density, J, in the original Ampere's law be changed so that the divergence of the curl of the magnetic field equals 0? The change of the current density, J, can be made by adding another current density, J prime, so that so that Ampere's law becomes Nabla cross B equals mu naught times J plus J prime. Then the vector calculus identity used by Maxwell, which says that for any vector B, the expression divergence of curl of B must be 0, gives divergence of curl of B is equivalent to 0, and then it yields on the right side mu naught times the divergence of J plus J prime, which equals 0. It yields divergence of J plus J prime, which equals 0. So it yields divergence of J plus divergence of J prime, which equals 0. The equation of continuity, divergence of J plus del rho over del T equals 0, and the above result then shows that the extra current J prime that must be added to Ampere's law must be such that the divergence of J prime equals the time derivative of rho. This expression shows that the additional term J prime depends on the time derivative of the charge density rho. With this expression for J prime, Ampere's law becomes nabla cross B, or the curl of B, equals mu naught times J plus mu naught times J prime derivative of rho. And divergence of curl of B equals 0, as required by the vector calculus identity. Now, he's saying J prime equals J prime times something, so it like I wonder if he's just changing it. Like, yeah, I guess. Can you scroll up just a little bit? So that last sentence, the above result then shows that the extra current J prime that must be added to make the equation balanced out, right? That's the point. He's fixing it. It must be added in such a way that the curl of J prime equals the time derivative of rho. Okay,
All
so
this without talking about the source of J prime, relative, even proximal relationship to J,
the
which I find
charge
objectionable.
density.
Yeah.
Okay, so okay, he basically added it like he's like, this is how we would make this right side 0. I see what he's doing. Okay, and how is this modification different from Maxwell's? The above modification is different from Maxwell's in that I still don't know what J prime is, but in that Ampere's law still contains currents and only currents, current densities actually, as observed experimentally. I consider it correct because no other physical quantities are added artificially, only currents. Also, observe that for vacuum where there are no charges, rho equals 0, and no currents, J equals 0, J prime also becomes 0 because it depends on the existence of electric charges. Ampere's law for vacuum becomes curl of B equals 0, which is completely different from that obtained by Maxwell. Curl of B equals his displacement current. Ah, okay. In Maxwell's modification of Ampere's law, the supplementary current J prime, which is equal to J prime times del rho over T, is not left as above, but it is expressed further through purely mathematical manipulations. So I wonder what the supplementary current is. I mean, if J is already the current density, what's J prime?
That's what I was wondering, and where it's coming from, how it's going to relate in terms of geometric, and none of that is addressed. Everything is assumed zero curl, and this dimensional. It's a one-dimensional analysis of a formula.
Well, I understand why he's doing the curl and the divergence, but I don't know what the J prime is supposed. He just says a supplementary current. I don't understand what's being introduced here. Like what? Because if the J is the current, then like what's the J prime? Like there's another current? I don't understand.
Exactly. A current density, right?
Yeah, of course, but coming from current being there. So, anyways, but it's further expressed through purely mathematical manipulations. This was shown in a previous page in the excerpt from Griffith's Intro to Electrodynamics, 1999, but I rewrite it here. Maxwell starts from Coulomb's law. The divergence of the electric field equals the current density over epsilon naught, because he uses for the case in which there are or the charge density or epsilon naught for the case in which there are charges, i.e., rho is not equal to 0. Note this because Maxwell afterwards claims that the modified Ampere's law that he obtains through its use is valid also for vacuum where rho equals 0. I will mention the condition rho is not equal to 0 with the vertical bar throughout the calculations made by Maxwell to remind the reader that the calculations are performed with this condition, rho is not equal to 0, and that the calculations are not possible if rho does equal 0. Okay.
How conveniently annoying. How to visually destroy a formula.
To show that in all these cases, or the charge density is not equal to 0. Okay, so assuming the charge density is not equal to 0, divergence of electric field equals charge density over permittivity of free space equals charge density, or yields the charge density equals because they're multiplying it out. Okay, so the charge density equals the permittivity of free space times the divergence of the electric field, which yields the time derivative of the charge density. And that's equal to the permittivity of free space times the time derivative of the divergence of the electric field. And that yields the time derivative of the charge density, which equals the permittivity of free space times the divergence of the derivative of the electric field, So it finally yields in the final form that the time derivative of the charge density is equal to the divergence of the permittivity of free space times the time derivative of the electric field. Okay. Comparing the divergence of J prime equals the time derivative of, because that's the same thing. So he's saying that, oh, I see what he's got here. Comparing the divergence of J prime is equal to the time derivative of charge density with the time derivative of charge density equals that expression found above. Maxwell observed that J prime must equal epsilon naught times the time derivative of the electric field. That's Maxwell's displacement current when the charge density is not equal to 0. He then introduced it directly into Ampere's law. So that's where it came from. So he's just postulating there's some supplementary current because we know that there's no current, right? There's no current. So there's a supplementary current. So this is the displacement current. Okay. The difference between Maxwell's modification of hold on. He introduced it directly in Ampere's law, obtaining the curl of the magnetic field equals the permeability of free space times J plus J prime, which becomes the curl of the electric field equals permittivity of free space times J plus the permittivity of free space, or permeability of free space times permittivity times time derivative of electric field. The difference between Maxwell's modification of Ampere's law and the one which I consider correct is summarized below. So on the left, we got the one we just read, whereas the vertical bar current charge density is not equal to 0 indicates Maxwell's displacement current term was obtained from the divergence of the electric field equals charge density over permittivity of free space, where charge density is not equal to 0. And then in his version, he's got instead of having this electric field component on the right, he just uses the J component, the J prime component on the right, where the divergence of J prime is equal to the time derivative of the charge density. So that's all that J prime is. All that J prime is the divergence of it is equal to the charge density. Okay. So he's basically saying that J prime itself is just a term representing charge density, whereas like in Maxwell's setup, he changed it and threw the electric field in there.
That was a lot of work just to get that far.
Yeah, well, I mean, you gotta figure it out, I guess. But yeah, because Maxwell basically converted this J prime stuff into an electric field and represented it with a field, whereas he's like, nah, the whole J prime term is actually just talking about the charge density. Okay. So the difference between the two is enormous because in general, in physics, the equations connecting different physical quantities are interpreted phenomenologically. That is, they must correspond to effects observed experimentally. As stated above, Maxwell's version of Ampere's law implies that a magnetic field B can be produced by a changing electric field E, and this is not observed experimentally. For a vacuum, Maxwell's modification of Ampere's law and Ampere's law modified correctly differ significantly, as shown in the table below. Oh, so on the right side, he's like, if the charge density is 0, and that means that J is 0, and therefore the curl of the magnetic field is 0. But on the left, if he uses Maxwell, the current density is 0, or the charge density is 0, therefore J is 0, but the curl of the magnetic field still equals this displacement current term. And he puts a little bar in there to remind you that this is only valid where the charge,
where there is a charge density, or one exists already, and some other thing is going on.
Yeah, so that displacement current term is only true with the bar there, where it shows that rho is not equal to 0. So that still corresponds to the situation where rho is not equal to 0. So that means in the equation reality would not correspond correctly in a vacuum, because in a vacuum rho is 0, so this equation wouldn't work. So that's what he's saying. He's like, Maxwell's equation would work in a situation where you have a charge density, because that charge that's in there will create an electric field. So you can relate the electric field to the magnetic field because there is a field there. But in a vacuum, there's no charge, and there has to be a charge for there to be a field, because a field comes from a charge. The charge is what creates the field. Okay. Wow. Math magic. But I understand what he's saying. This difference is due to the fact that Maxwell was inconsistent in his calculations. He used Coulomb's law with charges to modify Ampere's law, and then claim that the modified Ampere's law obtained from it is valid for a vacuum where there's no charges. In fact, this claim cannot be true because if the charge density is 0, then Coulomb's law becomes the divergence of the electric field equals 0, and it can no longer be used, it cannot be used anymore to find the expression for the charge density and for J prime as shown in the above derivation.
It flatlines the whole thing.
Yeah, because then the electric field would be 0 too. That Ampere's law for vacuum must be the curl of the magnetic field equals 0, and not the curl of the magnetic field equals Maxwell's displacement current, can be seen also from another fact. Remember that Ampere's original law read the curl of the magnetic field equals magnetic permeability times J, and that the term of Maxwell's displacement current was added by Maxwell to make it comply with the equation of continuity, the divergence of J plus the charge density equals 0, and with the fact that always the divergence of the curl of the magnetic field is 0. Obviously, these equations referred to regions of space where there were charges and currents. However, if we refer to vacuum where there is no charge or current, we observe that the equation of continuity becomes identical to 0, while Ampere's original law becomes the curl of the magnetic field equals 0 and satisfies the vector
Okay.
calculus identity.
Okay, go back one sentence on your scrolling. These equations refer to regions of space where there were charges and currents, but are no more. The current density and charge density are 0, but there is no context about the intensity of the currents that used to exist there, how long ago since they were not there, which polarity is the last thing you saw in the resonant ringing of counter space. There's none of that here. I mean, maybe I'm just being overly complicated, but yeah, there's a lot of context missing in the actual physics, I find.
Well, I think he's saying were because he's talking in past tense, because he says the equations referred to regions where there were. He doesn't say are because the whole sentence is past tense. He could also equally validly say these equations.
Yeah, okay. Yeah, different context, I guess. But still, it's not what it's what I'm not seeing here. It's kind of bothering me, but okay.
However, if we refer to vacuum, rho is 0 and J is 0, right? Current and charge and current 0. Then we observe that the equation for continuity, the divergence of J plus the time derivative of charge, equals 0. That becomes identical to 0, while Ampere's original law becomes 0 and satisfies the vector calculus identity, divergence of curl is 0. So, in the case of a vacuum, it is not necessary at all to modify Ampere's original law in any way, since it already satisfies all the necessary requirements invoked for its modification. Going back to what experimental evidence says, Ampere's law states that there must always be electric currents to produce a magnetic field. Even if the current density is 0, it is the supplementary current J prime that's not 0 that produces a magnetic field B. This supplementary
That's
current
so ambiguous.
This supplementary current is produced through the change of charge density. Okay. Such that the divergence of J prime equals the time derivative of the charge density. Okay. So he's saying that this charge density of space is changing, and that is what is producing the magnetic field. So even if there's like 0 current, right? If the current density is 0, right? There's like no moving charges or whatever. But this supplementary current has produced the change of charge density. Okay, so these equations always link the fields with the charges producing them and never omit them as important intermediaries between the fields. The correctly modified Ampere's law does not predict absurd, never observed phenomena such as that according to which a magnetic field B can be produced by a changing electric field E. Even if there is an equality of magnitude between J prime and Maxwell's term, as Maxwell showed, this does not mean that the electric field term, or the time derivative of electric field times electric permittivity of vacuum, can be replaced in the equations where J prime appears. Doesn't mean that, and then expect that a changing electric field will replace the physical effects of the of J prime, which is related to the charge density with respect to time. As a conclusion, Maxwell is not correct because in science, the equations we write should not be correct only dimensionally and quantitatively, but they must also correspond to observed phenomena. Substituting the electric field term for J prime in Ampere's law, although it's correct mathematically and dimensionally, it is not correct phenomenologically because the interpretation of that law, thus modified, will lead to absurdities not observed in the real world. Physics over math.
I'm not seeing a lot of dimensionality in there that he claims to be seeing, and incongruous dimensionality, but let's go.
I think he's talking about dimensional analysis in terms of units. Like that's what they usually mean, unit analysis. There are many situations in physics where when we replace physical quantities in different equations, obtain other equations that are correct dimensionally and quantitatively, and use them to calculate unknown physical quantities. But we cannot expect these manipulated equations to make sense phenomenologically, to see them in a true direct cause and effect relationship between the physical quantities that appear in it. As is the case with Maxwell's modification of Ampere's law, the equations manipulated by mathematical operations, even if the math is allowed, like correct, they bring together mathematical expressions which correspond to physical phenomena that have no direct cause-effect relationship and thus turn out to be absurd statements if interpreted phenomenologically. To give you an example, consider a spring that's hanging vertically. We know experimentally the spring will stretch because there's a force F acting on it. And if we express the extension of the spring, X, in terms of the force F as 1 over the spring constant times the force, but we can apply a force to the spring in another way. For example, consider a piston attached to the spring and a cylinder fixed to the ground. The gas in the cylinder contracts when cooled, and the effect is that the piston moves downwards, pulling the spring with a force. So, besides pulling forces F that may act on the spring, we have to consider another force F prime that produces the same effect. The original formula giving the extension of the spring then becomes X equals 1 over K times F plus F prime, according to the law of addition of forces, verified experimentally. Then we can measure experimentally how F prime changes with the temperature. Suppose that the experiments yield F prime equals negative R times delta T, where R is a constant, a gas constant, and delta T is the change in temperature of the gas in the piston, which shows that a negative temperature change produces a positive force F prime that stretches the spring. Now, the equations, X equals 1 over K times F, and X equals 1 over K times F plus F prime, and F prime equals negative R times delta T have been obtained experimentally and can be interpreted phenomenologically. But if we replace F prime in the equation for extension X, then we obtain X equals 1 over K times F minus R times delta T. See, he took the equivalent expression of F prime instead of F prime. And while that is correct mathematically, quantitatively and dimensionally, it leads to absurdities when we interpret it phenomenologically. For it says that a spring can be stretched by a decrease in the temperature. Maxwell's modification of Ampere's law has been obtained by a similar false method of theoretical investigation, and this is why it cannot be considered correct. I think that example.
Yeah, that was a great metaphor.
Yeah. How does this affect Maxwell's electromagnetic theory? Maxwell's theory remains unchanged if the equations are not used for vacuum. But for regions of space where there are charges and currents, Coulomb's law with charges leads indeed to the system of 4 equations, thus given here, which includes in equation 4 Maxwell's displacement current term. And as it will be seen later, they yield the equations of waves. Also, it will be discussed in what follows that equation 3, corresponding to Faraday's law, agrees with experimental observations, and therefore it can be written in such a form provided that due account is given to the fact that charges and currents must always be present. In other words, charge density and current density are not 0. However, Maxwell's theory changes dramatically if the equations are written for vacuum because of Ampere's law. Then you have the divergence of the E field is 0, the divergence of the B field is 0, the curl of the B field is 0, and the curl of the E field equal to the time derivative of the B field. It can be seen that Faraday's law, oh, you're getting fuzzy. Can you scroll down a little bit or turn your brightness up or I don't know what's going on. Why is it not bright? What's happening with the stream?
I'm not sure. What does it look like now?
fuzzy.
Give me a second. Any better?
A little better, yeah.
You have to keep your mouse hovering over the page in the column somewhere in order to keep the background fully white.
Okay, so it can be seen that Faraday's law, curl of electric field equals time derivative of B field, remains the only law out of the four claiming that a changing magnetic field creates another electric field in vacuum. But is it true? Right? Once we take away the charges. If we take away the charges, is that true? Well, the trouble with Faraday's law, when a magnet is inserted in a coil, what does the changing magnetic field of the magnet induce in the coil? Does it induce an electric field or does it induce an electric current?
Well, we happen to know it's a current because that is actually referred to as the magneto-electric effect.
Right. As mentioned earlier, I will discuss in the second section of the study another serious logical inaccuracy that I observed in the accepted laws of electricity and magnetism. It refers to the interpretation of Faraday's law of electromagnetic induction. Let's refer to another well-known textbook, Classical Electrodynamics, 1962, designed at its time for beginner graduate students. At page 170, we read, Faraday's law of induction. The first quantitative observations relating time-dependent electric and magnetic fields were made by Faraday in experiments on the behavior of currents in circuits placed in time-varying magnetic fields. It was observed by Faraday that dude, how were they doing this stuff in 1831? Wasn't that when we were all like horse and buggies and shovels and stuff back then? Like,
They were doing it definitely without the awesome oscilloscopes we have now, that's for sure.
Shout out to
well,
the
I'm just
Royal
talking
Society.
yeah, dog, I feel like history is such a lie, dog. How were they doing time-varying magnetic field precision experiments in the 1830s, dog? Like, they didn't have electricity back then. Like, they had discovered it. Like, what? They don't even make sense, dog. They didn't come out with
They
light
made
bulbs until the 1890s.
they made advantageous use of volta.
Yeah, anyways, sorry, didn't mean to divert. It was observed by Faraday that a transient current is induced in a circuit if A, the steady current flowing in an adjacent circuit is turned on or off. Okay. B, the adjacent circuit with a steady current flowing is moved relative to the first circuit. That's B. Or C, a permanent magnet is thrust into or out of the circuit. Okay. No current flows unless either the adjacent current changes or there's relative motion. That makes sense. Faraday interpreted the transient current flow as being due to a changing magnetic flux linked by the circuit. The changing flux induces an electric field around the circuit, the line integral of which is called the electromotive force. Cursive epsilon, I'm going to call it. It's a cool symbol. The electromotive force causes a current flow according to Ohm's law. Now, it's clear, I think, to everyone that the sentence, Faraday interpreted the transient current flow as being due to a changing magnetic flux linked by the circuit, means that the observed cause and effect is that a changing magnetic flux causes an electric current. Then, what is the reason for which it is invoked the existence of an electric field and an electric motive force? Quote again from the excerpt above. The changing flux induces an electric field around the circuit. The electromotive force causes a current to flow, according to Ohm's law. So, the production of an electric field is invoked to account for the movement of charges. To this it may be asked, but has Faraday not discovered a completely new effect here, in which the changing magnetic field pushes the charges? Why invoke the creation of an imaginary electric field to account for the movement of charges? Is this not an unfounded assumption? What was done here was pseudoscience because instead of faithfully encoding in mathematical formulas the effects as they were observed in reality, guesswork made its way into the explanation of what is happening in that observed process. The key point here is that Maxwell did not recognize that Faraday, with his changing magnetic field, found out another new way to make the electric charges start moving in a conductor. Faraday proved that electric charges can be made to move by varying magnetic fields, and not exclusively by electric fields as it had been believed before him. Maxwell considered that the electric charges in a conductor could be made to move only if the charges were under the influence of an electric field E. So he assumed that the changing magnetic field B must create an electric field equivalent to the curl of E first. So that they literally just inserted E in there. In fact, it can be seen from his works that Maxwell denied the existence of any force acting on a charge other than that force which was due to an electric field. Maxwell claimed, for example, that the force acting on a current carrying conductor placed in a magnetic field does not act on the moving charges, but on the conductor itself. What? He said that the force from the magnetic field, the magnetic force that acts on the conductor carrying a current, doesn't act on the charges moving through the conductor, but only on the conductor itself.
So then the rate of current induced is dependent on the permeability or the impedance of the conductor material.
By stating this, it can be said that Maxwell denied even the existence of Lorenz's force, whose derivation is based precisely on this very experimental finding. Oh yeah, the force on the charge from the magnetic field. That's Lorenz's law. See below the relevant excerpt from James Clerk Maxwell, A Treatise on Electricity and Magnetism, 1873. Okay.
Kind of
let's
hard to
Can you,
see.
like highlight? Can you highlight it? With
No,
like a dark
it's just
like an orange.
negative Ghost
I
Rider.
can just read the quote. I got it darker here if you
I
like.
got it.
You want to come back up? Okay, go for it.
It must be carefully remembered that it took a second that the mechanical force which urges a conductor carrying a current across the lines of magnetic force acts not on the electric current, but on the conductor which carries it. I'm gonna say that one more time. You gotta remember, guys, there's this mechanical force, right? Like, moving matter around. And that force, which urges a conductor carrying a current across the lines of magnetic force. Okay, so like the force that pushes the piece of metal, right? And the piece of metal is carrying a current, obviously, but the force that pushes the piece of metal, it acts not on the electric current, but only on the piece of metal itself. If the conductor, the piece of metal, be a rotating disc or a fluid, it will move in obedience to this force, and this motion may or may not be accompanied with the change of position of the electric current which it carries. But if the current itself be free to choose any path through a fixed solid conductor or a network of wires, then, when a constant magnetic force is made to act on the system, the path of the current through the conductors is not permanently altered. But after certain transient phenomena called induction currents have subsided, the distribution of the current will be found to be the same as if no magnetic force were in action. The only force which acts on electric currents is electromotive force, which must be distinguished from the mechanical force, which is the subject of this chapter. Okay. I'm thinking about the spinning discs and Faraday induction generator thing from Plenum right now. Observe the stark contradiction of Maxwell's words. If the current be free to choose any path through a solid conductor fixed in place or a network of wires fixed in place, right? Just metal sitting still. Then when that constant magnetic force is made to act on that system, then the path the current takes is not altered permanently. Okay? So if the current's free to choose any path, then when a constant magnetic force is made to act on it, the current path will not be changed. Can see the contradiction between that statement and J.J. Thomson's later experiments showing that electron beams can be deviated in vacuum by magnets. Oh! Or even the obvious contradiction between Maxwell's conception and the observations of Hall effect. Dang, this dude's cooking, bro. Yeah, that J.J. Thomson literally shoots an electron beam in a vacuum tube and then puts a magnet outside of it and moves it around with the magnet. Like, duh. It's not moving through a conductor. It's just charges moving through a vacuum, and it moved it with a magnet. Like, that's so obvious. Oh my gosh. Due to this erroneous type of reasoning, I think it is fair to say that Maxwell spoiled Faraday's law, and the mathematical equation called Faraday's law is not an accurate description of the observed phenomena. Exactly the same ideas as those propounded in John David Jackson, Classical Electrodynamics, 1962, can also be found in a more recent work from the Prentice Hall publishers, Intro to Electrodynamics, in 1999. At pages 301, 302, we find the flagrant. The author admits that Faraday observed an electric current induced in the circuit, and that before it was codified mathematically, the law was interpreted in terms of electric field. Electromagnetic induction, Faraday's law. Let's see the quote. Man, dude, this paper's freaking cooking, dude.
It's all about the dynamics and the attribution of cause. And here's just another classic example where mainstream has gone wrong.
In 1831, I agree, Michael Faraday reported on a series of experiments, including 3 that, with some violence to history, can be characterized as follows. Experiment 1. He pulled a loop of wire to the right through a magnetic field. A current flowed in the loop. Okay. Experiment 2. He moved the magnet to the left, holding the loop still. Again, a current flowed in the loop. Experiment 3. With both the loop and the magnet at rest, he changed the strength of the field. He used an electromagnet and varied the current in the coil. Once again, current flowed in the loop. The first experiment, of course, is an example of motional EMF, conveniently expressed by the flux rule. Epsilon equals negative d phi over dt. Okay.
That's the Roman
I don't-
E for the electromotive force.
Yeah. Electromotive force equals the change in flux with respect to time. I don't think it will surprise you to learn that exactly the same EMF arises in experiment 2. All that really matters is the relative motion of the magnet and the loop. Indeed, in the light of special relativity, it has to be so. But Faraday knew nothing of relativity, and in classical electrodynamics, this simple reciprocity is a coincidence with remarkable implications. For if the loop moves, it's a magnetic force that sets up the EMF. But if the loop is stationary, the force cannot be magnetic, because stationary charges experience no magnetic forces. In that case, what's responsible? What sort of field exerts a force on charges at rest? Well, electric fields do, of course, but in this case, there doesn't seem to be any electric field in sight. Faraday had an ingenious inspiration. A changing magnetic field induces an electric field. That's what he got from that. It is this induced electric field that accounts for the EMF in experiment 2. Observe the sentence. But can you go back up? Can you go just real quick before we go on? I want to see that picture again. So there's a loop of wire and there's a magnet. Okay. So there's the B is like a square magnetic plate, and then that other thing is a loop of wire. Okay, I got it. So we can go back down. I just needed to see it one more time. Okay. Observe the sentence. But if the loop is stationary, the force cannot be magnetic. Stationary charges experience no magnetic forces. In which the author, Griffiths, contradicts Faraday's very experimental finding, which says precisely this, that stationary charges do experience magnetic forces. They are set in motion by a changing magnetic field. Wow, so the textbook guy is just saying the wrong thing. Note also 2 other facts. Alpha, that even to this day, the fact that a changing magnetic field produces an electric field has not been proven experimentally. It has been the same status of assumption. Beta, that the author, Mr. David J. Griffiths, is not specific on whether the magnetic field in cases A and B is uniform or non-uniform. And this is important, because if the magnetic field is not uniform, then the gradient of some of its components may not be 0. This implies that such gradients are present in certain directions of space. And if the gradient of B is in the plane in which the loop magnet moves, then a force F equals m times the gradient of B, where m is the magnetic moment of the electron. It will act on the charges in the wire and cause the production of the induced electric current in it. Okay. So if the gradient, now the gradient, if you think of a gradient, that's just like how like the values change over across space. Like it might be 10 here and 8 here and 6 here and 2 here and 0 here, right? It like, changes. It's not uniform through space. But if the gradient is not 0, so if it is changing, This implies that gradients are present in certain places, certain directions. And if the gradient of the field is in the same region of space through which the loop is moving, then there will be a force produced that acts on the charges in the wire, and it will cause the production of an induced electric current through the wire. Okay. Even if...
Did you catch their desperation to integerize the analysis through the use of M?
Yeah, the magnetic moment.
Yes, cunningly slipped in there.
Even if the magnetic field is assumed to be uniform, there is still the possibility that the movement of the loop of wire to the right through the field, or the magnet to the left holding the loop fixed, may create a magnetic field gradient locally along the body of the wire. Yeah, there will be a gradient created, and that gradient will drive a force. Okay. The explanation given in other textbooks resemble those in the excerpts given above, with the difference that they use unscientific terminology to explain why Faraday's law is written in terms of induced fields instead of induced currents. Or they offer no explanation at all, mixing the notions together as if an induced current were equivalent with an induced field. See the two examples given below. Of Cengage Learning, published for 2010, Physics for Scientists and Engineers, Modern Physics. I'm pretty sure I've used that exact textbook, just not that edition. As a result of these observations, Faraday concluded that an electric current can be induced in a loop by a changing magnetic field. Okay. The induced current exists only while the magnetic field through the loop is changing. Okay. Once the magnetic field reaches a steady value, the current in the loop disappears. Okay. In effect, the loop behaves as though a source of electromotive force were connected to it for a short time. It is customary to say that an induced EMF is produced in the loop by the changing magnetic field. Oh, wait, a source of electromagnetic field or electromotive force? Is EMF electromagnetic field or electromotive force?
Yeah, it's EMF in this context. You're talking about the electromotive force. And yes, it's about the intensity of the field at the location of the conductor being changing over time.
Okay. As a result of these observations, Faraday concluded that an electric current can be induced in a loop by a changing magnetic field. It is customary to say that an induced EMF is produced in the loop by the changing magnetic field, so an electromotive force. Okay. And then here's a second textbook. The first quantitative studies of time-dependent electric and magnetic fields were performed by Faraday in 1831. He discovered that an electric current arises in a closed wire loop when it is moved through a magnetic field. The induced voltage is proportional to the rate of change of the magnetic flux. Okay. Yeah. The sign is fixed by the Lenz law, implying that the induced currents and the magnetic flux associated with it are directed such that they oppose the change of the external flux. The law is generally valid. In the second example, no explanation at all is offered as to why the observed electric current was changed into an induced voltage. Yeah, that doesn't make any sense. Okay. In my opinion, rather than trying to explain the above experiments by invoking the magnetic force for the case moving loop or stationary, for the case of a moving loop and a stationary magnet, or the creation of electric field for the case of a stationary loop and a moving magnet, they should have been translated in mathematical language in a form that expressed the fact that any relative motion of the magnetic field and the charges creates a force on the charges. A possible way to achieve this would be to generalize the formula for the magnetic force, F equals Q charge times V cross B. Wait, are we talking about Lorentz now? Through the addition of new terms that account for these phenomena, its generalization can be done by observing that V equals the dr over dt, change in distance over time, and that it can be rewritten as F equals Q times dr dt cross B. The generalized formula would be of the form Q times d dt r cross B. It can be seen that this formula yields Q times V cross B plus Q times R cross the derivative of B with respect to T. And that is composed of two terms, the original one and that corresponding to Faraday's changing magnetic field. Huh. Okay. The the time derivative of B does not necessarily have the direction of B, because the time derivative of B is equal to that. Okay. Oh, the total, yeah, the dB dt equals del. Okay, so you got the partial derivative with respect to time. Okay. So he's just adding up the partial derivative and the total time derivative, which can be rewritten as the total time derivative of B equals the partial time derivative of B plus the partial derivative of B, X, Y, and Z over del X, Y, and Z times U. The expression, that is the Jacobian matrix. And then he gives the matrix right there, 3x3 matrix. Okay. Whose rows are the gradients of the components of the magnetic field with respect to each axis. It follows that the acceleration of charges by time-changing magnetic fields can be explained either by the term Q times R cross dB dt, whose significance is at present not known, okay, or in a more straightforward way based on the idea that a time-changing magnetic field might produce a gradient of a magnetic field along the path of the charges. This implies that the charges accelerate not because they are electrically charged, but because they have an intrinsic magnetic moment. Therefore, the force that is responsible for the acceleration of charges in a time-varying magnetic field is then the magnetic force, which acts on any magnetic dipole that's placed in that non-uniform magnetic field, and that's given by the expression the force equals the magnetic dipole times the gradient of the magnetic field. I mean, he's making sense here. The possibility that in electromagnetic induction, the electric charges are set in motion by the magnetic field gradient caused by the varying magnetic field receives a very striking support from the fact that it gives, in its turn, a consistent and unexpected explanation of the empirically derived, but never accounted for satisfactorily, rule of Lenz regarding the direction of the induced currents. For consider two parallel conductors 1 and 2 with extremities A, B, and CD, respectively, when an electric current of intensity that's increasing from 0 to I is sent through the conductor on the left, 1, from B to A, which is from the bottom to the top. The magnetic field that's produced in its vicinity will have a gradient from C to D, because at any instant of time, the field at D is greater than at C, so the magnetic field increases in the direction from C to D. Therefore, the charges in conductor 2 on the right will, under the action of F equals a magnetic moment times the gradient of the magnetic field, be pushed from C to D, which is opposite to the inducing current I and is in accord with observations and with Lenz's rule. When the current in the conductor on the left is of constant intensity I, there is no gradient of a magnetic field produced in its vicinity in the direction of the conductor 2. So then there's no current that's produced in the conductor 2 on the right. It's only when the current in conductor 1 is reduced from intensity I to when the current is reduced from intensity I to 0, the gradient of the magnetic field is from D to C. So the charges in conductor 2 will be pushed in the direction from D to C or in the bottom to the top, i.e. in the direction of the inducing current. This is also in accordance with the observations and with Lenz's rule. So even if the circuit's broken, the movement of charges will still take place. The charges moving in a broken circuit under the action of the changing magnetic field causes them to separate and gather at the ends of the gap in the circuit. The electrons gather at one end, making it negative and leaving the other end charged positively. It is this movement that creates a momentary electrostatic field, E, inside the conductor. The mechanism may be detailed as follows. Man, that's so, see, he's like saying a magnetic field does it because it works even in a broken circuit. Because, I mean, like an electric force wouldn't work because you can't have, an electric force implies like a current. You can't have a current in an open circuit.
Well, he's only referring to the moment at which it opens where I is returning to 0.
Scroll back up a little bit. At the moment it opens? If the circuit's broken, yeah, okay. Like it was closed and then it opens. Okay. The charges move.
That is, quote, the change in J, right?
Yeah. So the charge is moving in a broken circuit under the action of the changing magnetic. Okay, yeah. The mechanism may be detailed as follows. When the current, J of T, and the charge density, rho of T, change in the conductor on the left, then Ampere's law gives the magnetic field in the conductor on the right. Now, That's in terms of J and rho. Now, number 2, the time-varying magnetic field creates a gradient along the second conductor on the right because the total time derivative of the magnetic field equals that expression. This gradient of B causes the charges in the conductor on the right to move because of the magnetic force. The conductivity of the conductor on the right affects the resulting force acting on each charge in it. The resulting acceleration of each charge is proportional to the magnetic moment times the gradient of the field minus k over the conductivity. I'm assuming k is some constant, and for the material. And the distance traveled by each charge along the conductor will affect the final charge density rho at the ends of the conductor. Okay, so however far each charge travels will affect how much the charge density is at the ends. I mean, that makes sense because they're spreading out. Okay, number 5, the charge density at the ends of the conductor produces an electrostatic field in the conductor. Okay, so you got at opposite ends of the conductor, you got charge densities, okay, that are different. And because you have different charge densities at the two opposite ends, it will create an electrostatic field inside the conductor, and you can find the magnitude of it using Coulomb's law. Okay, because the gradient of the field will equal the charge density over the permittivity of the vacuum. Okay, there's the vacuum popping up in there. Wow, you would think it would be. Wow. Okay, it can be seen there. Oh, that book. It wouldn't be the. Yeah, it wouldn't be the permittivity of the material because the field isn't like actually residing in the material. The field is residing in space. Oh man, that makes sense. It can be seen, therefore, that the production of the electric field in the conductor can be related to the time-varying magnetic field. So an equation of the type, the curl of the electric field equals the negative time derivative of the magnetic field, which is equation 3 in Maxwell's set of equations. It can be written, provided that due account is given to the fact that charges and currents must always be present. In conclusion, Faraday's observations, strictly speaking, can be summarized in the statement that there is a force acting on an electric charge whenever there's relative motion between the charge and the magnetic field. Below, I have tried to show diagrammatically the difference between Faraday's original discovery and its mathematical rendering. So Faraday's original discovery was cause, changing magnetic field, effect, movement of electric charge. Faraday's discovery was reinterpreted by the artificial insertion of an electric field and electromotive force in the cause and effect chain. So it then became cause, changing magnetic field, intermediate things, Y, electric field and electromotive force, effect, movement of electric charges. So the equation below, given in the Prentice Hall book from '99, corresponds to the interpreted version of Faraday's law. The curl of the electric field equals a negative magnetic field time derivative, partial time derivative. Observe that no induced current appears in this equation. Faraday's law has been transformed into an equation between two fields. It does not mention or require the existence of any static or moving charges, and this is not related to what was observed experimentally. Man. So there's a recourse to history. It says, I have tried to track back the origin of the confusion as to what's being induced in a conductor by a changing magnetic field. Is it an induced electric current or is it an induced electric field? And I found that this confusion is indeed due to Maxwell. It is known that Faraday has not written any mathematical equation describing his observations related to electromagnetic induction. Or to be more precise, Faraday called the effect he discovered magnetoelectric or magnelectric induction, as can be seen in experimental researches in electricity in 1849.
There it is.
And has always stated in his works that what is induced is an electric current. For example, Faraday stated one of his quantitative observations in terms of induced currents as follows. These results tend to prove that the currents produced by magnetoelectric induction in bodies is proportional to their conducting power. Another example is Faraday's enunciation of the condition in which electromagnetic induction takes place. Although it will require further research and probably close investigation, both experimental and mathematical, before the exact mode of action between a magnet and metal moving relatively to each other is ascertained, yet many of the results appear sufficiently clear and simple to allow of expression in a somewhat general manner. If a terminated wire moves so as to cut a magnetic curve, a power is called into action which tends to urge an electric current through it. But this current cannot be brought into existence unless provision be made at the ends of the wire for its discharge and renewal. So it has to be hooked up to something. Got it. Okay. If a second wire move in the same direction as the first, the same power is exerted upon it, and it is therefore unable to alter the condition of the first. For there appear to be no natural differences among substances when connected in a series, by which, when moving under the same circumstances relative to the magnet, one tends to produce a more powerful electric current in the whole circuit than another. But if the second wire moved with a different velocity or in some other direction, then variations in the force exerted take place, and if connected at their extremities, an electric current passes through them.
Sort of physical common sense. Eh?
Yeah, Faraday's numerous experiments were published in a series of 3 volumes titled Experimental Researches on Electricity, and they constitute the reference material Maxwell consulted when building his theory. For example, Maxwell's first article on electricity and magnetism was titled On Faraday's Lines of Force, and in it he attempted a mathematical description of the effect of electromagnetic induction observed by Faraday. In this article, Maxwell referred to the following excerpt from Faraday's works. The general principles of the development of an electric current in a wire moving under the influence of magnetic forces were given on a former occasion in the first and second series of these researches. It will therefore be unnecessary to do more than to call attention at this time to the special character of its indications as compared to those of a magnetic needle, and to show how it becomes a peculiar and important addition to it in the illustration of magnetic action. Observe that Faraday spoke again in terms of induced current. The general principles of the development of an electric current in a wire moving under the influence of magnetic forces. Okay. Electric current in wire moving under influence of magnet. Okay. Below I reproduce magnet makes current. Okay. Below I reproduce the relevant excerpt from Maxwell's article on Faraday's lines of force, in which reference is made to the above idea of Faraday. Faraday has shown that when a conductor moves transversely to the lines of magnetic force, an electromotive force arises in the conductor, tending to produce a current in it. If the conductor is closed, there is a continuous current. If open, then tension is the result. If a closed conductor whoa, wait, bro. I didn't realize that. If the wire's open, then you feel like the wire dragging. It drags against the metal because the earth gets the magnetic field. But if you close the loop,
This is all about open loop approach to charging a capacitor by motion of a magnetic field against conductors.
Yeah, because I mean,
You
you
see
know how you
that
move.
if the other end is a capacitor, then it's considered open circuit.
Well, like if you move like a piece of metal past a magnet, like it drags, right? You got the magnetic drag or whatever. That's the tension, I guess, right? But
Yeah, impedance,
it,
reluctance to be charged at all. Yeah.
but he's saying like if you close the circuit and you move it, then it, instead of like all this drag, it produces an electric current. So that drag tension force is converted into current. Okay. If a closed conductor moved transversely to the lines of magnetic induction, then if the number of lines, that's the whole quote, I guess. He's getting just that first part is what he wanted. Observe that Maxwell writes the subtitle on electric currents produced by induction. But in the text, he erroneously claims that Faraday has shown that when a conductor moves transversely to the lines of magnetic force, an electromotive force arises in the conductor, tending to produce a current in it. This is clearly an unfounded assumption on behalf of Maxwell, because it's clear from the paragraph of Faraday's work to which Maxwell refers that Faraday made no such statement. As you can see, Faraday did not claim an electromotive force arises in the conductor, but he merely claimed that an electric current is produced in it. H. Maxwell's equations and his wave equation with honesty. It is often stated that Maxwell's equations yield the equations of electromagnetic waves in vacuum. By this, it is meant that Maxwell's equations are valid for regions of space where there are no charges or currents, and that the electric and magnetic fields that compose the electromagnetic wave are not produced by any charges whatsoever. In other words, that the electric and magnetic fields that compose the electromagnetic wave induce each other in vacuum without the mediation of electric charges static or in motion. In truth, the said equations can be obtained for regions where there are charges and currents, and no reason can be given why they should be valid for vacuum as well, since textbooks never mention the fact that Maxwell's famous equations for electromagnetic waves can be obtained even without the conditions ρ and J are 0 for vacuum. Few students suspect that they are being lied by omission. Just look at the derivations of the equations of EM waves as given by one of the standard textbooks, the 1999 Apprentice Hall book. In regions of space where there is no charge or current, oh, it literally says it, Maxwell's equations read thus, and it gives them, okay, same ones we've been dealing with. They constitute a set of coupled first-order partial differential equations for E and B. They can be decoupled by applying the curl to 3 and 4, and they give the forms we were looking at earlier as well for 3 and 4. Or since the divergence of E is 0 and the divergence of B is 0, then the gradient squared of E and the gradient squared of B yields those. We now have separate equations for E and B, but they are of second order. That's the price you pay for decoupling them. In vacuum, then, each Cartesian component of E and B satisfies the three-dimensional wave equation. Gradient squared F equals 1 over V squared times second partial derivative of F with respect to T. You can interpret the two differential equations for E and B in any way you wish. The ambiguity is so great you consider them to be vibrations of a line of electric or magnetic field fixed at its ends, or of a line with one free end, or even without ends, closed loops. Or you can consider that they are waves that travel in space at infinite distances. I mean, what criteria should we use when we choose between these possibilities? The fact that no experimental evidence exists that the electric and magnetic fields induce each other in vacuum, where there are no electric currents and no electric charges, would prevent an honest scientist from interpreting them as being waves propagating freely in empty space. However, the significance of the expression that yields the speed of light in vacuum, speed of light equals 1 over the square root of magnetic permeability times electric permittivity of free space, is not lost. This is because the wave equations for E and B can be obtained even in regions where there are charges and currents. Here's the proof. Same book in 1999. We consider a region of space in which there's a charge density ρ and a current density J. The equations are thus. Same equations, 1 through 4. We proceed in the same way as in the said textbook, and we apply a curl to 3 and 4. A curl of 3 yields, so that all of this, which means the divergence of the divergence of E minus the gradient squared of E equals the negative magnetic permeability times the partial time derivative of the current density minus the magnetic permeability times the electric permittivity times the second partial time derivative of the electric field. Or by using this, you get equation M1 right there. Now, the curl of 4 yields this equation. Okay, the curl of the curl equals the divergence of the divergence minus the gradient squared equals the curl of that, Maxwell's displacement terms, or Maxwell's displacement term and the magnetic permeability times the current density. And then, or you get this one. So we have that, or by using 2, you get the final equation M2, which is the gradient squared of the magnetic field equals the negative magnetic permeability times the curl of J plus the mu times epsilon times the second partial time derivative of B. Observe equation M2 becomes the equation of a wave for the magnetic field if the curl of J equals 0 without being necessary to use the condition for free space with no charge and no current, where ρ and J equals 0. Since the equation was obtained from the normal set of Maxwell's equations, with charges and currents, it follows that even in Maxwell's theory, we cannot say that this is a wave corresponding to vacuum. Also observe that equation M1 becomes the equation of a wave for the electric field if the gradient of the charge density is 0 and the time derivative of the current density is 0. These equations tell us that there can be charges, but no charge gradient. And there can be currents, but no time changing currents. So constant currents and constant charge density for this wave equation to obtain. Okay. it can be seen that the electromagnetic wave equations are valid for matter containing charges and currents, and no reason can be given for considering that they represent waves in vacuum. What then is the significance of the speed of light? Since the vibratory behavior of the magnetic field and the electric field are obtained from Maxwell's equations with currents and charges, the significance of c cannot be other than it is the celerity with which an electric charge acts on another electric charge in its vicinity. It's the speed of electromagnetic electric interaction, charge interaction. C is the speed of charge interaction. In conclusion, in this article it was shown that Maxwell's theory of electromagnetic waves contains an unfounded assumption, a faulty method of theoretical investigation, and it makes a prediction that's contrary to observations. These are 1. The unfounded assumption that a changing magnetic field induces an electric field. In fact, a changing magnetic field is observed to produce an electric current, not an electric field. And there's a great difference between electric current and electric field. Number 2, the assumption that a changing electric field induces a magnetic field. This was derived by Maxwell through a faulty method of theoretical investigation, and no such effect was known in Maxwell's time, and no experiment has been made since that proves this assumption. And 3, the prediction that radio waves and light are composed of entangled electric and magnetic waves that induce one another in a vacuum. No experiment revealed that radio waves and light have a structure containing electric and magnetic fields. Wow. No experiment has revealed that radio waves and light have a structure containing electric and magnetic fields. Although it seemed an easy and straightforward matter to accomplish, Faraday failed in his attempt to change the plane of polarization of light traveling in vacuum by the application of strong electric and magnetic fields. Only when the polarized beam of light passed through glass of great density could this be accomplished, and even then by the application of a magnetic field only. Further, Faraday initially applied the magnetic field perpendicular to the ray, believing this would change the direction of the plane of polarization. But by not obtaining any positive result there, he then placed the magnetic field parallel to the direction of the ray, and he finally obtained the change he was looking for. But then, how can this result be reconciled with the theory in which light is considered to be composed of 2 transverse electric and magnetic fields? It does not seem that the magnetic field applied by Faraday and the magnetic field of the light ray vibrating perpendicular to it give a resultant in a different plane. Wow, so he puts the magnet next to it, and the field produced by the magnet is extending parallel in the same direction as the traveling light ray, and it polarized it. But when he shot it perpendicular so that it crossed across the light ray, it didn't polarize. That's so interesting. It was shown in this article that Maxwell's theory is valid only for regions of space containing electric charges and currents, and it fails to give any account whatsoever of the nature of the waves traveling in a vacuum at great distances from their original source, where neither charges nor currents exist. With these missing parts, Maxwell's theory cannot be considered an established scientific theory. The author, himself a physics teacher, considers that his duty is not only teaching the syllabus and asking the students to believe theories, but also to look for the proofs that exist and support the theories propounded in the textbooks. With all that's been discussed in this article, can an honest teacher stand in front of a student and teach him that Maxwell's theory is proven beyond doubt?
Nay, I say. Nay.
Dude, this is a dope. You know what's so crazy, Alan? This is what you chose for reading night, and unrelated. Earlier, I spent like an hour and a half roughly researching the relationship between electric fields, electric potential, between current electric fields, electric potential, and charge. Okay. And this it syncs up with this pretty much perfectly, and I didn't even know you were reading this tonight. So what I found is like the way the mainstream explains it, I mean, he's right on point. But when we talk about circuits, when you ask like what is producing a current, like let's say you have, you've got a loop of wire, and on that loop of wire you hook a light bulb, and then you attach the 2 ends to the 2 posts of a voltage source like a battery, or let's say an ideal voltage source. A current goes through the wire, of course. But if you ask what produces the current, it says, well, there's an electric field in between the posts of the battery or the voltage source. And when you attach the wire, basically that electric field gets sucked up into the wire and moves through the wire. And that's what that electric field moving through the wire is what pushes the charges around. And you're like, okay, so what produces the electric field then? Since the electric field is what creates the current. And they're like, well, the electric field is produced by the electric potential. And you're like, okay, what's that? And it's like, well, the electric potential is when you have a whole bunch of charges on one post and a whole lot less charges on the other post, and there's this difference in the charges. And so the electric potential creates an electric field. And it's like, yeah, but what about there being charges there that are just chilling? There's just charges chilling on the metal. Like, what about that constitutes a field being created? Like, what's the field, right? But it gets too entangled. And it's like, okay, so there's this electric potential, and the electric field is created by this difference in potential, and the differences in potential is due to the arrangement of the charges. So therefore, it is the charges directly in their arrangement, the arrangement of these charges, that creates this electric field. Like, you can have an electric field, you can have a static electric field just from charges sitting somewhere, right? They don't have to be flowing, they can just be sitting still, and it still will create a static field. And of course, if the charges move, it's a time-varying electric field. But either way, the charges are what creates the field. Then I was like, okay, well, if that's the case, then I don't understand like how you can say that that it's this way, because let's think about a vacuum. We know that in a vacuum, right? In the vacuum, we can induct electricity wirelessly. There's wireless induction of current through a vacuum, and it's like, yeah, I mean, you can shoot electromagnetic waves through a vacuum, and in this model, it brought up what he's talking about in this article, like the electric and magnetic waves, the electric and magnetic fields induce each other. I'm like, yeah, but where's the electric field coming from in the vacuum? Like, you put this electric field in there. Where's the electric field coming from? Because there's no charges in a vacuum, right? There's no charges. So where's the electric field coming from? It's like, well, there would have to be charges like outside the vacuum. Like, you would use a device and put charges on it and then induct the field through the vacuum. And it's like, okay.
Trust me, bro.
Yeah, I mean, you have to have charges. The point is, you have to have charge. You can't have a field without a charge. It doesn't charge. Fields don't exist by themselves, right? And then the other problem, like, and this extends into like the medium, right? If that potential, because the arrangement of charges is what creates the field, right? So if you create a big enough potential, a big enough voltage, because that's what potential is voltage. If you create a big enough potential between two ends of the vacuum, right? Then you can, if you get a super, super, super high voltage, you can actually exceed the permittivity of the vacuum itself, and you can what's called the breakdown of the vacuum, or the ionization of the vacuum. Now,
Catastrophic failure of the potential.
yeah, of the material to act as a dielectric, and then when that happens, the vacuum becomes ionized, and guess what happens? Charges appear in the vacuum. Like, literally, electrons will spawn in the vacuum. They will spawn because the vacuum is said to get ionized. Now, when you investigate this, like, how can a vacuum be ionized? Because when we talk about ionizing something, typically we're talking about a fluid, like a gas or something like that, right? Like a fluid, a gas. Like hydrogen gas or something, or helium gas, you can ionize it, right? Turn it into plasma. You get hydrogen plasma when you ionize it. Well, a vacuum is said to be empty space. How are you ionizing nothingness, right? And that's when they interject and they say, well, there are, of course, vacuum fluctuations. And so when the vacuum is ionized, it's not being ionized in a traditional or classical sense, like when you think of a medium. What's happening is energy is being extracted from the vacuum fluctuations, and when enough energy is being input into them, then they are transformed into charges, and they become they become electron-positrons pairs, and the current pops up until the voltage is gone or whatever, and then they self-annihilate with each other. So you can literally, if you apply enough voltage across a vacuum, you can cause electrons to spawn. You can ionize a vacuum. Now, if that doesn't tell you...
In the active resolution of that charge, that's really all that you're looking at through free space. Yeah.
That doesn't tell you that there's a medium in there, because ionization is a property of like somethingness, not nothingness.
Matter, yes.
Yeah. If that doesn't tell you that there's something in the vacuum, I don't know what will.
Nope, there's nothing in there but a field of math.
Thanks for sharing the paper, dude. That's dope. I think I have it, but I don't know where it is. So can you like drop it in the? Is it already dropped? Did you drop it already?
Yep, it's at 102. Well, that time doesn't sound right. I'll link it to you again. 1 sec. Copy link. There you go. Yeah, dude, thanks for reading and breaking that down as you went along. I've been wanting to follow up on that paper for a long time, but like as it trickles down to the stuff past the radio propagation, it's like over my head. So that was awesome that you and Stone were able to break that down as we went along.
No worries, bro. Do you have the original? I guess I could find it since it's Ionel Descu. I could probably find it. I was gonna say the non-highlighted version. I'll say the highlighted version, but I want to be able to share it.
Yeah. It's on. I don't
want to send it to somebody and be like highlights by Alan pops up everywhere.
No, all his stuff is on ResearchGate. I'm pretty sure, so you can find it there.
Ionel Descu.
Yeah, he's also got a YouTube channel. He does some experiments and stuff. Oh, Vixra, yeah, that's where he's at. Oops.
So you guys may remember last week when we reviewed the Musha paper, the explanation of the Biefeld-Brown effect, and this guy named Takaki Musha. We were reading his 7-pager there. I wanted to get back to it if you guys have a minute.
Absolutely.
It was right in the middle of the paper, and I do realize that everything I'm about to say has appeal only to a very small percentage of the crowd, but I think it's still worth examining to a superficial degree, simply for the benefit of everybody to understand what these people are up to sometimes when they write these papers. That they don't necessarily give you the straight goods even about what they're doing themselves. Or if they are, they're telling us how little they actually know about it, which I find ironic as a possible option. So I'm just going to share my screen here.
Wait, this one is 2013. Yours is a different one. The one I looked up was November 2012. Sorry, go ahead, Stone. Where'd you get the 2013 one out?
Couldn't tell you.
What the heck?
All right, so I'm up, and we're here looking at the Musha paper, and he gets down into the middle of it all and starts to talk about the thing that he's using in terms of circuitry to create, quote, generating AC pulses here, like figure 3. Now, there is earlier occasion in the paper where he suggests that he would be using DC hitting the capacitor in the experiment itself, where he's trying to produce this change in motion according to figure 1, where the scale balance is going to change based on the rate of change of charge between the two plates themselves, the capacitive plates themselves. And he claims that he's using circuitry like this to create AC pulses. So what I wanted to do first for you guys is show you the correct way, I guess a more correct way, to even draw what he's got here in figure 3. I'm assuming you guys can also see my mouse moving.
Yes, sir.
Is that correct? Okay, great. So, yeah, figure 3. Here we go. This is those two illustrations drawn, again, with the power on the left always flowing to the right, the negative polarity of the power always flowing through the bottom end of the diagram to represent, ground, We assume that's the lower part of things that happen, and that the more charged, more positive things happen at the higher parts in the diagram. Well, in the little box in the middle here, what he's suggesting is that this is a massive step-up transformer. And first off, I have a problem that he would be using 12 volts as a supply source in order to produce large voltage deltas across his capacitor. The experimental capacitor that he's trying to, this is the piece he has on the scale where he's trying to change, the weight readout on the scale based on how fast he's charging this and discharging this. He's suggesting that he's going to use a square wave to hit this MOSFET or transistor, but more efficient to use a MOSFET for anybody who pays attention and that kind of thing, to hit the primary coil with 12 volts, and then a whole bunch of volts are supposed to come out this way. And I wanted to show you the difference between the two. He's suggesting that there's some kind of AC function going to the capacitor in both of these cases, where the impulse is on the first half of the wave, and here it should be the same, because all you're doing is changing how the voltage goes through the primary. Here he's allowing the positive to go downward through it. Here he's allowing the positive to go upward through it. That's the only difference between these two. However, he has the diodes flipping to match what might be coming out of the coil, unbridled by any other governing circuitry at all. And in both cases, he shows the positive side down on the capacitor. So I don't know exactly what this guy's dealing is. You know what I mean? What he's driving here is diagrammatically nonsensical, even when you draw it correctly. That's the main gist of what I wanted to point out. It strikes me that he's just not telling us what's going on. So I wanted to talk about some alternatives and how you would do what he wants to claim he's doing in his paper to produce AC changes in the coil, etc. Here we're seeing that the first impulse, first half of any unit of time, this is the switch that's opening. So really we're allowing positive to go from this voltage supply through, arrow pointing down. This is a PNP MOSFET. This would also be PNP because we're switching on the low side. The positive is coming through it. Okay, in the first case, rather, bringing it back, we have positive coming through, and this primary is inducing motion in the coil. Okay, and then the second half of the waveform, we're letting positive come down from the other source through this primary, where it would then, of course, do it the other way around. That is an option that I would say, okay, that's valid to produce AC function in this capacitor. Another way that you could do that is what I'm showing here, which is essentially the same as the first one, but we're doing it with a single source. That on the first impulse, we're allowing positive to come through the middle and then out to the negative. And then on the second half of the impulse, we're allowing positive to come through here and then out to the negative. So really, the pulse is going this way and then that way, and it's push me, pull you, exactly the same you would expect here. But frankly, I would do neither of these, regardless of how good they might look. Because of the phenomenon of electrical inductance, the delta H here in henries. When you have many turns in a coil, it takes longer to induce current within the coil, proportional to the number of coils in it. Over here, you can blast away at high frequency, but if it's too high, you're not even going to get your bang for the buck out of all of this coil over here, because it will still be ramping up by the time you hit it with the opposite polarity, so to speak. And it's just not a fast, snappy way to go when, according to what he says in the paper, the goal is a really fast voltage delta across the plates. In the cases where we're looking at what's going on here, I always wonder what people use in generating the signal, which governs the power of the circuit. And in very analog terms, my favorite chip, and is also one favorite of John Bedini's, was the SG, as in signal generator, 3525 chip. It's a 16-pin DIP. This is about 3/4 of an inch long by about 1/3 of an inch wide on the black and less than 1/4 inch thick. That's how big these guys are. These are the pin assignments, but we're only concerned with pins 11, output A, and pin 14. Output B. This is the internal, the end piece, I guess, of the internal, much larger schematic that is explaining everything that's going on inside this chip, including the opportunity to use a dead zone. And what I mean by dead zone would be in this form here, that there would actually be a little bit of passing through zero before continuing on to the opposite polarity. Again, coming down here, we would have an on and then off, but we would have a little bit of time here at zero before the other one goes this way. We don't want that according to this guy's goals in his paper. So we're only going to be looking what's going on here. You could draw mentally one big box around this and view this as an oscilloscope reading as to what's going on with the chip. That literally, this one puts out a positive pulse, it turns off, and then this one puts out a positive pulse. And this is a nice creative way to wire exactly what we were showing you over here, where we're splitting the primary. He's showing you how to do that with a single power supply, where this is implying negative, a ground connection, very cheaply detailed. But that's what's going on there. I would do none of this part here. This is the problem, is that it takes so long, inductively speaking, to get this thing to react, to operate at sufficiently high frequencies to achieve the very high delta V over T that you want here in order to produce the change on the scale most effectively. This is what I envision. Like, it's kind of like, it's not like I've tested this circuit out. This is more a case of, hey, I saw this in a movie once and I'm sure it would work. That the original circuitry is exactly as I've drawn here. We're pumping the primary, it's going this way, and then it's going that way through the coil. These two are the addition to what's going on here, in that when the current is being blasted out the top of this guy, it has only one place to go, really, out of its two options, diodally speaking, is down here to charge this one with negative down. And the same way vice versa coming through this diode, that the only thing permitted, this coil, only thing permitted to do as far as circuit path would be through here. So we have two oppositely charged capacitors that you can just run them up to the sky. Sky's the limit, because they're not doing any actual work themselves, and they would go sky high. You'd have to have very high voltage ratings in them. And then you take them one at a time, use a separate timing, not this timing here, a separate timing entirely, which could be much faster even than what you're hitting with the primaries over here. You could take it out and run it through here back to its own cap. So this would be the up initial pulse coming through here, through the cap, down and out through this diode to release the energy out of this cap, and then vice versa. The second half of the pulse would be here, where this cap would be draining out in opposite polarity through the cap and then through that MOSFET and complete itself here. So this would be the second half of the circuit. For me, I think much higher delta V's over T here can be achieved through capacitive discharge as opposed to inductive discharge. I hope that makes sense to people. That when you learn about electromechanics and the dynamics here that are actually going on, and you take a look on the scope at what happens to something like this with a ton of turns, and what happens to a big old fat cap with a big charge in it when you are given a low resistance place to spend it, other than this, lower voltage state cap here, that this one will rush to become the same charge as this one, and then it'll flip and rush to become the same charge as this one. And the only thing that's going to slow it down is the impedance of this little short conductor. The resistance here is the only thing that's going to slow down your current, as opposed to what it's going to take to constantly flip the polarity of this coil back and forth, in or out of resonance, regardless. So I hope that makes sense, that I would be going about what Musha did in an entirely different way. And if he was really being honest with us, he would have shown us a lot more of the picture of what he was actually doing so that we could replicate and prove him right, so to speak. That it doesn't look like this garbage here. It just doesn't. This is not what he used. I guess is the short of what I'm trying to say there. Any questions at all about what I just showed you guys?
No, I wouldn't even know where to begin, but thank you.
Oh, fair enough. All right. Just wanted to be complete.
No,
it's,
that's really
just for
interesting.
context.
That's
You know
really
what I mean?
interesting, though. Yeah, no, for sure. That they, basically put like a fake diagram in there so that you can't reproduce it. Is that kind of like the purpose of that?
They did. There's some serious fuckery going on there. And when last week, when we were reading through this paper, I'm looking at it going, what the hell is he talking about? You know what I mean? That doesn't produce AC, and it's all drawn fucked up. Like what's going on? So, I needed to point that out. It's been bugging the shit out of me.
Well, I'm glad you did.
All right, guys, back to your regularly scheduled programming.
All right, lads. I think we're going to end out on a brushtail ad from Lily.
If she's there.
Dude, unlucky.
And out pops Galatrax, orb in hand. Recommend. Oh, go ahead, Lily.
Oh, sorry.
Do we
I don't
have?
know why.
We do have an ambassador. All right.
No, it took. Sometimes this mic, it doesn't respond. Like I keep pushing my finger, and it doesn't respond at all. Oh, Galatrax, if you have a testimonial, go ahead, and I'll go after you, or whatever.
No, you go. I thought you weren't there. You go. I was gonna free ball.
Oh, I'm so sorry. Yeah. So, folks, yeah. I used to have this medical condition, and it has a Latin name, and I think Stone would understand the Latin name. It's called aetatis excessibus via hilaritacitis. It's also known as volitare via hilaritacitis.
Mm-hmm.
And what it is, huh?
Mm-hmm. Yeah, I'm familiar with it. Yeah.
Yeah, it's a very rare medical condition, let me tell you, folks. But anyhow, long story short, what it means is that it's a buoyancy or a floating that's caused by excessive cheerfulness. And so what happens is that now I live in the Pacific Northwest where it drizzles all year round almost. And then the brief summer that we have, it's super, super hot and sunny. So I have to always carry an umbrella when I'm out. And so anyways, if I see like squirrels running around or some, bird doing a mating dance for his mate or anything cute like that in nature, it just makes me so cheerful that I just start floating. Because, all the neurotransmitters in my brain, they create a certain frequency. As you know, our bodies are more electric than they are chemical. And so it just causes this floating. Anyway, so I can just kind of float up into the air like 10, 20, 30 feet, which, could be kind of dangerous. Long story short, I go to the park often. There's a park nearby where I live. And so I always feed the birds there, and there's loads of crows. I've gotten to know this murder of crows, which is a group of crows. I've gotten to know them really well. And so luckily, every time my medical condition kicks in, these crows have been rescuing me. They pull my umbrella back down and then bring me down to earth. Anyway, long story short, when I started drinking brushtail coffee, I suddenly and magically was cured of this rare medical condition, which is called aetatis excessibus via hilaritacitis. So I'm so grateful to brushtail coffee because it actually healed me of this very, very rare medical condition.
And as a Brushtail custodial service representative, I would just say that it may or may not have cured that, but we've heard similar testimonies here at Brushtail that it has cured offense. It's the Latin.
Oh yeah,
What was the name of that
the
disease again,
I,
Galatrax?
Oh yeah, it's
Sounded like you said asbestos dust.
yeah,
it's
yeah, all of it.
Itatis excessibus via hilaritacitis.
Exactly.
Yeah.
Well, I'm very glad that Rush
In
Tail
English, you
Coffee-
might call that emotionally induced buoyancy.
I'm glad that Brush
You
Tail was able to
got
cure
it,
that for you.
Stogie.
Allegedly. All right,
Yeah.
lads. That wraps up our evening.
Check your mic
Thank you
volume there, Alan.
Thank you
Oh.
everyone for the presentation, and thank you PHOG for reading.
How does it sound now? I was tilted away a little bit.
I think you're still a bit low.
Shoot. Well, I'll have to fix it in a minute. But all right, I'm going to do the outro stuff. So tomorrow will be Flat Earth Fridays, episode 114 or 13. I can't remember. See you guys tomorrow for that. And then next Tuesday will be a follow-up presentation to the Twin Paradox, I think. So we'll see how that goes.
We got one more thing tomorrow night slated, right, Alan?
Ooh, I forgot about that. Tomorrow night, the world premiere of Stone's new video on centrifugal acceleration in the orbit of the moon in relation to the mass of the sun, and how they say that it just so happens to work out and the centrifugal acceleration cancels out all the extra force from the sun. Well, you know, our boy Stone, he wouldn't let a diagram in a paper from last week go. You think he's going to let orbital mechanics go? So no, he's plotted out all the vectors of force to show exactly what would happen if any of the dynamics asserted about the heliocentric model were true. So that'll be awesome. We're going to premiere that tomorrow, hopefully on Flat Earth Fridays, but if not, we'll do it before then.
I think we should just hard code it right now for 7 Eastern. Because they're supposed to start at 8 Eastern, right?
Yep, got you. So yeah, we're going to do a premiere
That
tomorrow.
gives us some time to partay.
Awesome.
Yeah, so be here or be rhomboid.
Yep, be here tomorrow at 7 p.m. Eastern for the premiere of that. And then we'll get into Flat Earth Fridays.
7 minutes of ho, 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 ho.
Dude, I'm looking forward to it. And for those of you who aren't familiar, you can go to Minute Physics on YouTube and look at his latest video about the moon and centrifugal acceleration, and to get a kind of idea of what we're talking about here. And then I'm sure Stone will have a recap of the conversation that he had on Flat Earth Fridays a couple weeks back to kind of give a recap and preface to the.
It's actually a recap of the discussion between Pizzo and Peter.
Oh, the follow-up to the follow-up.
Handy-dandy diagram about the sun and the moon and the earth there, and discussed the centripetal attractive forces there. And it was Peter who said, oh, yes, that all works out because you have to add the centrifugal forces in too. And that's why they all move the way they do. Yeah, sure.
Nice.
Oh, is that the video entitled "The Moon's Orbit is Weird"?
I think so. Yes. Yeah. That's it. Yep.
All right, I'll put that in the chat.
Thank you, sir.
Yeah, you'd be surprised at the timing of that video coming out right about now.
Put that in the YouTube chat for anyone listening.
Oh, thank you, sir. All right. See you guys tomorrow, 7 p.m. sharp.